I want to talk about understanding molecular machines from a somewhat fundamental level, and briefly for what they can be used. And of course, I'd like to thank Fraser and Melissa for inviting me to both to the conference and to speak here. So I've always had, or for a long time, have had the perspective that maybe the best use of molecular machines is to perform molecular rather than macroscopic tasks. And so the goal that I'll describe is to use a molecular machine to make a high-yield product, even though the product is much less stable than the substrate from which it is synthesized. Now, basically, that means I want to make something that's very expensive from things that are cheap and with a fuel or energy input that we can design. And the idea is that the molecular machine will serve to couple external energy and drive the non-equilibrium process of synthesis against equilibrium. Now here's an example using the kinds of mechanical bonded molecules with which we're all familiar, I think. And I refer to this as an externally driven chemical synthesizer. What is the pointer thing? Is that here? Oh yeah, here. So if we can arrange it so there's an equilibrium between the reaction being catalyzed, which I've taken a simple disproportionation reaction, A, B goes to A plus B, and it has an equilibrium constant. And if we can design a catalyst based on a mechanically bonded molecule that drives this reaction faster than it would go in the absence of the catalyst, and also design this such that we can put in energy externally, and in this case, I'm going to add and remove a ligand. We can design the kinetics and the thermodynamics such that even at equilibrium, I give this cycle a net tendency to go around either clockwise or counterclockwise, depending on how it is that I've arranged these. And so that tendency will drive the reaction away from equilibrium, and you can show a rather significant change in the stationary position. Now, this is another implementation where we have a catalysis-driven process. And here, the idea is the same ligand, but we want to do it autonomously. We want to simply add the molecule that's being catalyzed. And of course, I have in mind Dave Lee's FMOC chloride conversion to dibenzofulvene, which we'll see later on. But the catalysis can also drive this around either clockwise or counterclockwise. Now, if we go back, the key design principle for this externally driven machine is to design these equilibrium constants, to design the energetics, the energies of the different states, such that when we apply an oscillation of the concentration of this ligand, that it makes it go around clockwise. And that's something that we've done, has been done in the past quite easily. That design principle is very, very different than the design principle we need for the identical molecule, but when it is being driven by catalysis. The simplest design principle here, if I want to make this go around clockwise, is to make this very slow. To make, for example, this reaction highly specific for product, and this reaction highly specific for substrate. And then if substrate is in excess and product is in deficit, the reaction will go around in this direction, and then product will dissociate. And so I can give it a clockwise tendency, and it turns out that that clockwise tendency does not depend in any way, shape, or form on the free energies of the different states. Back here with the externally driven process, the free energies of the states are the design principle. You have to design different free energies to make it go around. Here, it is the kinetic specificities that is the design principle. Even though these molecules are identical and we're using the same ligand to drive them. Now let's step back a little bit and to some work that I did a long time ago with a colleague, Baldwin Robertson, on looking at the effect of oscillations, in this case oscillating electric fields, but it doesn't really matter, on an enzyme, with the idea being that the enzyme interacts with the reaction. Of course, it's a catalyst. It binds substrate and releases product, and at equilibrium, of course, it's doing it both ways equally, but it also interacts with the environment. The enzyme is big. It has many degrees of freedom. We can design, if we could design enzymes, we could design enzymes that have particular degrees of freedom that can be stimulated by whatever kind of input energy we would like. And what we were able to show is that as I drive these kinetic barriers only, that the stationary state of the chemical reaction being catalyzed is different than the equilibrium. And it's different from the equilibrium by an amount that is I don't know where that came from. It's the exponential of the work of the energy absorbed, averaged over all possible trajectories. So this is quite interesting, I think, because I have these parameters that tell me how the activation barriers are being influenced by the field. Normally, at equilibrium, of course, activation barriers are irrelevant. Here, however, if I choose to make this activation barrier significantly influenced by the field, but this one uninfluenced, it drives the reaction to favor product. If I make this one strongly influenced and this one uninfluenced, it drives it strongly in favor of substrate. In other words, this term, which I messed up, can be either greater than 1, less than 1, or 1, depending only on the kinetics, not on the thermodynamics of the process. And here we see that indeed, with those, the equilibrium I set to be 1/2, and so if I have the barriers modulated equally, nothing happens. There's a whole bunch of dissipation, but you get no flow. If, on the other hand, I have the forward barrier influenced, but the backward barrier not, I get a significant enhancement of product relative to substrate. If, on the other hand, I have the second barrier influenced, but the first barrier not, I significantly enhance substrate relative to product. So we see that in non-equilibrium situations, kinetics, activation barriers play a much greater role than they do under normal under equilibrium circumstances. And here's just to illustrate exactly the same thing. What we have is absorbed energy from the oscillating parameter, electric field in this case, which can either be fruitfully used or dissipated. And so, for example, we can see lots and lots of dissipation, but no fruitful use, as in this case. Now, how can this be used in the context of mechanically bonded molecules? Well, it is now autumn. We are back in class, and so I'm going to give you all a small test. Here are two molecules with the only difference, so just to define the terms, the blue and red are recognition sites, and they interact differently with the CBP-QT ring, And these are speed bumps. The bumps are the things that determine the activation barrier. And of course, at equilibrium, the fraction on blue and red for both molecules is exactly the same, because the energetics is entirely dependent on the redox potential and whether you're on, and the interaction between the CBPQT and the two recognition sites. When we began to oscillate the oxidation and reduction back and forth, and this is a kinetic factor, so we're going to have some fast relaxation times, some slow relaxation times. If I oscillate slowly, nothing interesting. If I oscillate fast compared to everything, nothing interesting. The interesting stuff comes in the window between the slowest relaxation time and the fastest relaxation time. Now, we can simply by logic, if we had a lot of time, figure out what's going to happen in the presence of an oscillating redox potential. They're different for the two molecules, because here we have an electrostatic barrier, and so depending on whether this is reduced or oxidized, the energy of the barrier changes. Here we have a steric barrier. The energy of the steric barrier relative to the CBPQT ring is more or less independent of whether it is the CBPQT is oxidized or reduced. And so we see, and you can use these energy diagrams to figure what's going on. I'm not going to go through this because of time, but lo and behold, with the electrostatic barrier, we favor strongly the molecule to remain on the blue, because when it's oxidized, it can't get off, because the barrier is large. With the, on the other hand, with the steric barrier, we accentuate the ring being on the red. So we can control the behavior in the presence of an oscillating redox potential by changing not the thermodynamics, but only the kinetics. Now, let's change gears a little bit, and I want to point out that when we take a Michaelis-Menten enzyme, okay, we normally don't write the back reaction, but I'm going to do it because, as I said, my middle name is microscopic reversibility. And if you erase that, you can't enforce it, and so let's not erase it. And we're going to solve for the fraction of molecule in the liganded form, and it's better to write it E sub L rather than E sub S, because when it's bound, it loses its individual identity as substrate and product. And we're going to look at the ratio at steady state, not with oscillations, but just at steady state with delta mu being 0 or not. And well, when we do the arithmetic, of course, we write the rate constants in, which are the 2, and the rate constants out, which are the 2 out, the off rate constants. Remember, the off rate constants are unimolecular, or it's first order. So if I have a ratio of these two, k plus 2 and k minus 1, it's independent of the free energies. Well, I can use the fact that we have this relationship, that we know that the overall equilibrium is not changed, to derive an expression to use this. This is equal. These are just the same things. But we identify something that depends only on the kinetics. This factor, which I've defined as the kinetic asymmetry factor, depends only on the ratio of the off rates, independent of the free energies, and e to the minus delta mu, which is the energy of the substrate to product. So let's, and of course, if we take delta mu equal to 0, it does not influence at all. That asymmetry factor is irrelevant. If, on the other hand, we take the system to be away from equilibrium, and I took a mild one, delta mu equal to 5, depending on the ratio of the off rates, I can either have everything in the free form, everything in the bound form, or in the middle, no change from the equilibrium case. And it's just freshman arithmetic. Now, one more test. This is based on Dave Lee's lovely catalysis-driven rotor. So I'll tell you what this reaction is in a moment. But I have put in two design principles here. And, well, nature put in one. But I've arranged it such that in the absence of the ligand, the substrate product ligand, that the green site is favored relative to the blue site, and hence this equilibrium constant is shifted to the left. And I've arranged it such that the ligand repels the CBPQT ring, causing it to want to be on the aqua site. So this equilibrium constant is shifted this way. Now, from that thermodynamic reasoning, we could come up with a cock and bull or story about how the chemical energy forces the ligand on, a power stroke moves it from here, then it releases because there's little or no product, and we complete a cycle. The other design principle is based on steric hindrance. And so if you look, you see that this reaction is going to be slower when the ring is in the proximal site than when it's in the distal site. So we have arranged a situation where thermodynamics and a sort of wrong way of looking at things, incorrect, will predict that it goes around clockwise. But a correct expression using microscopic reversibility predicts that it goes around counterclockwise. Experimentally, it goes around counterclockwise. So you can see this by doing so here we have those two kinetic asymmetry factors. One is inverse, and so we have this simple expression, independent of the free energies of the states. The direction of rotation of this molecular machine does not depend on how we arrange the free energies. It depends on how we arrange the energies of the transition states. And so I will finish speaking of Fraser's pump. Here is the pump molecule. So remarkably, there is a very strong interaction between a reduced form of the CBPQT and a reduced form of Viologen, such that this has a very stabilizing free energy. In contrast, when we oxidize, this is very unstable. However, this is a steric speed bump. This, on the other hand, is electrostatic. So you see that we have a situation where this barrier depends on whether the CBPQT is or is not oxidized. This barrier does not. And consequently, if we think about it, we can get it to come on, then oxidize it, force it off, but it can't go this way because that barrier is too high. And so kinetically, it has to go this way onto the collecting chain. And so at the end of the day, by cycling between reducing and oxidizing conditions, we can end up with rings on the collecting chain, even though they are much less stable than they would be in the bulk. So a highly non-equilibrium structure has been created. Now, and this is the description in terms of the equilibrium constants for the reduced, for going on to the Viologen, and the equilibrium constant here, which is very much shifted in this direction, but it's also blocked energetically. And in the oxidized form, this is the favored reaction because that Viologen is highly repulsive to the oxidized CBPQT, and this is blocked kinetically. And so even though K1 red times K2 red is much less than 1, K1 ox times K2 ox is much less than 1. which says everything ought to be in the bulk, what we end up with is a kinetic scheme that is K1 red times K2 ox, which is greater than 1. And that's the steady state. We have a lot of rings on almost quantitatively. Now, this is the goal. We would love to be able to couple this with a redox reaction, which is a redox couple, such that it is autonomous, such that we don't have to raise and lower the redox potential, but we can just put these molecules, red 1 and ox 2 and red 2 and red 1 and ox 2, let it go as in a catalyst and end up with the rings on the collecting chain. Can we do that? Yes. Not yet. I mean, not experimentally. But when we do the kinetics, we see that, in fact, the probability to be on the collecting chain has nothing whatsoever to do with the energies of these two states, even though in the previous case it had everything to do with those two states. And in fact, it has only to do with being able to control this half reaction and this half reaction, such that when you are in the bulk, that the first half reaction occurs, but not the second, because of kinetics. We can't change the equilibrium constant. And when you're on the intermediate, the second reaction occurs, but not the first, because of kinetics, not because of thermodynamics. And so we will end up with a path that describes this, and we can write the steady state ratio of assembled to disassembled in terms of the kinetic asymmetry factors that have been discussed. So, to summarize, away from equilibrium, kinetics is essentially everything. It is much more important than we have been led to think based on all of the many years of thermodynamics and equilibrium. And so finally, I'd like to thank Chuyang, Jean-Marie Lane, well, all of these people. You can read that as well as I can. Now, I'm sarcastic. I'm sorry. I would love to thank the NSF and NIH for supporting the work, but I can't because they didn't. And I was at Chicago back in the day when pink sheets were pink sheets. And this is actually from a pink sheet. The work described is focused on an important system and is very interesting. It seems, however, that the author proposes to do mostly thinking, and then in a striking truth in advertising, it is not clear that NIH should support thinking. And those are the words. I'll leave them there. Okay, thank you very much.
Yeah, thank you a lot. So I won't steal any time from asking questions. Yeah, here's one.
So the statistical thermodynamics that you discussed there, it applies for quite large assumptions, right? And take advantage of molecular nature of the machines. How do you deal with examples where thermodynamics, for example, second law is not observed? Because the fluctuation in the local system of molecular machine can go to lower entropy.
Okay, I warned you, I'm sarcastic. There was a paper in PRL, Dennis Evans' group, entitled Violations of the Second Law on Short Time and Small Length Scales. If you look at the paper and ask, what does it really say? It is that if I take a graduate cylinder, put some dirt in it, such that it's finely particulate, go out and look at the position of one of the particles of dirt, go out, have a cup of coffee, and come back, I might see that the one particle of dirt that I looked at is a little bit higher than it was before I went out. And that is quote unquote a violation of the second law. It increased its potential energy. From where did it come? The thermal noise of the bath. But this is not something that people... you don't have to worry about situations where the second law is not observed, because the second law is always observed. And remember that there are two statements of the second law. One is that of Clausius, that there is a function called the entropy, which never decreases. Okay, fine. Yes, that was a situation. The relevant one for all of these molecular machines is Kelvin's statement, which is that there can be no cycle in which work is done on the environment, with the only other change being the cooling of the system. And that is a cyclic thing. It cannot, Kelvin emphasized that it had to be something that was reliable, that it could happen in a cyclic fashion. That never happens. So individual trajectories, if you take the idea of Dennis Evans of this violation of the second law of thermodynamics, think about it. Every chemical reaction is a violation of the second law. Why? Because you start in a low energy state, and at some point you get to a high energy state we call the transition state. Well, where did the energy come from? Where did the energy come? The thermal bath, of course. And if you could trap it, you would have violated the second law. But this is not what Kelvin means.
So, Dean, I think you could write a book on this kind of thing. Anyway.
So the central thesis of yours is that for these systems, it is the kinetic state that one should worry about, not the thermodynamic state. So given that, it suggests adaptive and actually, even more interestingly, evolving systems, the systems that will self-evolve to suit the task. And I wish you would talk about it.
And I wish I
Maybe
could.
not.
I could talk about it, but it wouldn't make any sense. I wish I could sensibly talk about it. And obviously, these are things that I am thinking about, and hopefully other people are thinking about. But I do think it's that your observation is right on. That away from equilibrium, we have to look at kinetic stability rather than thermodynamic stability. And if you go through, for example, any of these situations that I put up, you can look at the lifetimes. What is the lifetime of a molecule? It is the sum of all of the off rates. And find that, okay, yes, I've stabilized the system not because the equilibrium has been shifted, but because the sum of all of the off rates of this state is much smaller than the sum of the off rates for this other state. Well, so I favored this one relative to that one, just by kinetics.
Hey, Dean. It may be a stupid question, I apologize if it is. When we're talking about moving from, say, low energy starting materials to higher energy products, we're obviously processing energy to do that. It's a dissipative system overall. Would I be correct in saying that?
Can you repeat it?
Absolutely. So we're going from low energy starting materials to higher energy products.
Mm-hmm.
Obviously, the system processes energy to achieve that. It's
Yes.
dissipating energy. Can you write an expression that gives you the maximum efficiency?
The maximum thermodynamic efficiency?
Yeah.
Yes.
So how much energy you have to process to get to X kilojoules per mole?
Yes, but you're not going to be happy with it. It's one. It is one. You're exchanging free energy for free energy. There is no fundamental limit lower than one for the efficiency with which chemical energy can be converted to stabilizing a reaction. And also remember that the molecules with which Fraser has published a lot, for example, the pumps, those CBPQT rings are kinetically amazingly stable. As I understand it from Chuyang, you can put them in the refrigerator and come back many months later, they're still there. So it's not like you have to continually process energy. So the amount of energy necessary minimally to go from the bulk to the collecting chain is the free energy difference between a molecule on the collecting chain and the molecule in the bulk. That's how much energy you have to put in with the redox.
Just to reiterate my question, that means that you can process energy, you can generate a more ordered system at no cost?
You can, absolutely. I mean, so long as you're changing free energy to free energy. So you're taking the free energy of the order of the redox molecules to converting that into the apparent increase in the order of the pumps. Yeah.
I'll catch you in the break.
Okay.
Okay, I think on that note, we'll thank Dean.
Okay.
So first of all, this is
We'll
their
switch
mic.
from